Hello friends, in this video we will see the continuity equation in 3 dimensions. So I have chosen this fluid elements and here these are the coordinates of the fluid elements. Now we have decided the length of the fluid element, width of the fluid element and height of the fluid element. So dx, dy and dz are the length, breadth and height respectively. We have chosen the 3 directions. This is x direction, this is your y direction and this is your z direction in which the fluid is flowing. So here actually your fluid is flowing in all the 3 directions. So we have to choose the velocity component in all the 3 directions. So u we have chosen the velocity component in x direction, v is a velocity component in the y direction and w is the velocity component in z direction. Now we will write the rate of mass flow equation along this face, then this face and finally from the top face here. So now one by one we will see how we are writing the equation of rate of mass flow along all the faces. So now mass in per second, this is nothing but this is rho into velocity in x direction into area of this A, B, C and D. So here the velocity in x direction is nothing but this is u and area of A, B, C, D, this is this dimension and multiply with this dimension here actually. So this dimension is nothing but this is a dz dimension and this dimension is nothing but this is your dy. So now here we have write the equation accordingly, rho into u into dy into dz. Now mass of fluid leaving the phase EFGS per second, this is nothing but whatever be the mass in plus rate of change of mass. So the mass in, this is same rho u dy into dz plus change in mass along the x direction. So del upon del x into rho u dy into dz into dx. So now here we will find how much gain of mass in x direction. This is nothing but the mass in minus mass out. So here we'll write the equation mass in rho u dy dz minus mass out rho u dy dz minus dou upon dou x rho u dy dz into dx. First two terms are same, so it's cancel out and the rest of the remaining part of the equation is minus dou upon dou x into rho u dy into dz into dx. Now here u, this is the function of x, so rho and u will keep it inside the bracket and whatever be the rest terms we have will take out of the bracket. So minus dou upon dou x into rho u dy into dz into dx. This is the net gain of mass in x direction. Now similarly we can see here same fluid elements we have and we will see the direction of fluid flow in a y direction. So now mass throw CGHD per second, this is equal to rho into v. This v, this is a velocity component in y direction into area from where your fluid is entering. So the area is this way, so this is your dx into dz. Now mass throw ABFE per second. So ABFE, so from here the mass is out. So that would be mass in plus rate of change of mass in y direction. So the final equation will be rho into v into dx into dz plus dou upon dou y rho into v into dx into dz into dy. Gain of mass in y direction is, this is a mass in from this face minus mass out from this face So mass in rho v dx into dz minus rho v dx into dz minus dou upon dou y rho v dx dz into dy. Again both will cancel out and the final terms is rho that is equal to minus dou upon dou y rho v dx into dz into dy. Again this v, there is a function of phi, so rho and v will keep it inside the bracket and the rest terms will keep out from the bracket. So minus dou upon dou y rho into v dx dy dz, this is the quantity of mass gain in y direction. Now if the fluid is flowing perpendicular to this plane or perpendicular to the screen, so now here your mass is entering from this area B, W, G and F, so and out from this top. So now here mass through B, C, G, F, that is equal to rho into velocity in z direction, that is W, into area from where your fluid is in. So this is your dx into dy. Mass out from AEDH per second, this is what is the mass in from here. So rho W into dx into dy plus rate of change of mass in z direction. So dou upon dou z rho into W into dx into dy into dz. Gain of mass in z direction is mass in minus mass out. So here again both these two terms are same, so it's cancel out and final terms will be minus dou upon dou z rho into W dx into dy into dz. W, this is a function of z, so we'll keep inside this bracket and the rest the constant terms out. So dx into dy into dz, these are nothing but this is the volume of your fluid element. Now here once we know the quantity of mass gain in each direction, we'll find out the net gain of mass in all the directions. So that is the equation, is a net gain of mass. This is a minus dou upon dou x rho u plus dou upon dou y rho v plus dou upon dou z rho w dot dx dy and dz. We know the mass is neither created nor destroyed in the fluid element. So here whatever be the net increase of mass per unit time, that should be equal to rate of increase of mass of fluid inside the element. So here mass of fluid in the elements, that's equal to rho into dx dy and dz. Now here we'll find the rate of increase of mass. So this equation will change dou rho upon dou t into dx dy and dz. We'll equate this rate of increase of mass with net gain of mass. So here we'll write both the equation. So minus dou upon dou x into rho u plus dou upon dou y rho v plus dou upon dou z into rho w dx dy dz, that is equal to dou rho upon dou t into dx dy dz. Dx dy dz, this volume, this is known as dv, this is the same, so we'll cancel out from the both side and the rest equations dou rho upon dou t plus dou upon dou x rho into u plus dou upon dou y rho into v plus dou upon dou z into rho w, that's equal to 0. This is the continuity equation without any assumptions here. Now As per the conditions or as per the assumptions, we can again remodify our equation. Suppose we are saying the flow is a steady flow, then in this case, whatever be the parameters are changing with respect to times, we will keep it as 0. So here this is your continuity equation, and here we are taking this condition. We have a flow is a steady state flow, so dou rho upon dou t it should be cancel out. So now I will cancel out here. So remaining equation, dou upon dou x, rho u plus dou upon dou y, rho v plus dou upon dou z, rho w, that is equal to 0. So this is equation is applicable when our fluid is flowing with a steady condition. Now here if we'll add one more condition along with steady state flow, if fluid is incompressible in nature, so we know in the case of incompressible nature, the density is constant. So here we can take out the density from this bracket. So now the next final equation for all these conditions, this is a dou upon dou x into u plus dou v upon dou y plus dou w upon dou z is equal to 0. So this continuity equation is applicable when fluid is steady state and incompressible fluid. So here actually what we are considering all the 3 dimensions. Suppose if the fluid is flowing in the 2 dimensions, so any one of direction we can cancel out. So here for the 2-dimensional flow, the equation will be dou u upon dou x plus dou v upon dou y, that is equal to 0. So is it in this video? I hope you have cleared the concept of continuity equation in 3 dimensions. Thank you friends. If you like it, then please share and subscribe with your friends.